Okay, so welcome to today's lecture. So last time we took a detour from our information theoretic studies, pure information theoretic studies, and we wanted to see some places in areas other than information theory where the one-shot entropic quantities, or in general, information theoretic quantities play a major role. So we took a problem from communication complexity. Okay, so let me go back. Oops. Yeah. Okay. You can see this, right? Yeah. So we defined the communication complexity model. So this model was actually first defined by Andrew Yao in 1979, and it actually sparked a huge body of research, still very active. Okay. For many reasons. Yao's original motivation was VLSI design, prove lower bounds for circuit size or number of wires for computing some function on a VLSI chip. Okay. So the simultaneous message model is as follows. So this is the simplest model of communication complexity. So there is some function which we would like to compute, f of x comma y. It depends upon two inputs that I'm calling x and y. Now, in this simultaneous message model, there are three parties: Alice, Bob, and referee. Alice is given an input x, Bob is given an input y. Okay. Now, because Alice doesn't have access to y, she cannot compute f just from x alone. Similarly, Bob cannot compute the output of the function from y alone. Now, what they do instead, Alice and Bob, is that they just send messages to a referee. So just one message. Alice sends a message m, which depends on x. So I'm calling this mx, and Bob sends a message n that depends on y to the referee. The referee cannot see the original x and the original y. Okay, so the referee only gets his input, the pair of messages m comma n, and from that the referee has to output his guess of what the function value should be. So the action of the referee is a function f hat of m comma n, and what we want, let us say we are talking of a private coin randomized protocol. So the internal computation of Alice can use private coins. In other words, the mapping from x to mx is a private coin algorithm. The mapping from y to ny is a private coin algorithm. The referee can use his own private coins. All the private coins are independent of each other. Okay. And the private coins are private. Alice's private coin can only be seen by Alice. Okay. So the referee outputs something, and what we want is for every x comma y, the probability that the output f hat is equal to the true output f should be greater than 1 minus f hat. Okay, so here the probability is coming from the private coins of Alice, Bob, and f. Okay, so this should hold for every input pair x comma y. So there is no probability distributions that we are considering over the inputs for this correctness definition. We may consider probability distribution over the inputs in our lower bound analysis. Okay, but for the definition of correctness probability, it is worst case over inputs and averaged over private coins. So the function that we are concentrating on is equality. So equality of x comma y. X is a bit string of length n. Okay, right? X belongs to 0, 1 to the power n. Now equality just means that the bit string x is equal to the bit string y. In other words, the xi equal to yi for all locations I. Okay. Yeah. And we argued that if you're looking at deterministic protocols for equality, there is a lower bound of n plus n bits from Alice, n bits from Bob. Note that n plus n is always a trivial upper bound for any problem because Alice can send her entire input to referee, Bob can send his entire input to. And then what we did was we started thinking of randomized algorithms. So first of all, we were looking at public coin algorithms. So in the public coin algorithm, Alice and Bob shared a public coin R. Okay, and then okay, so because all the randomness is coming from public coin, we can assume without loss of generality that Alice's function is deterministic. So she sends a message m, and we gave a very simple protocol with complexity 1 plus 1, 1 bit from Alice, 1 bit from Bob. So what was that? So Alice's message is x dot r. Okay. R is this public coin. It's a bit string of length n. Okay, it's a uniformly random bit string of length n. And the message is the dot product of x and r. So dot product is done modulo 2. Okay. Similarly, the message of Bob was y dot r. And the referee just did the simple thing. If the two message bits that he receives are equal, he will declare x equal to y, or else he will declare unequal. Now, of course, if x is equal to y, the two message bits will be the same. So the referee will succeed with probability 1. And then we argue that if x is not equal to y, then the probability that x dot r equal to y dot r, okay, where the probability is now coming from the random choice of r, is exactly half. Okay, so the referee will declare unequal with probability half. So if you look at the success probability in all cases, it's either 1 or half. Okay? And now we said that we'll repeat this protocol some t times. Okay? So instead of one public coin R, we have R1, R2, RT. Each one is a bit string of length n. Okay? Each Ri is chosen uniformly and independently of the others. Okay? And then the message becomes t bits long. So the message will be x dot R1, x dot R2, x dot R3. Similarly for Bob. And the referee will answer equal if and only if all the message bits coming from Alice equal the corresponding message bits coming from Bob. And then you can easily see that the error probability of the protocol, which was half earlier, okay, the worst case error probability, that half quickly goes down, the half becomes half to the power t. Okay. So far so good, Hari? Aditya?
Yes.
Yeah. Okay. So let's see. Okay. Next. So then the question was, okay, so this is public coin. What can we do for private coin? Okay, so, and that's where we spent the remaining part of the lecture. And this turned out to be non-trivial. And this was explicitly asked as an open problem in Yao's original paper, like equality function, private coin. What is the complexity? Okay. So public coin, we know the complexity is order 1, the communication complexity. Okay. What about private coin? Then we started developing ideas which would give a better private coin protocol. So from 1979 till 1996, nobody knew anything better than N plus N for private coin. So in 1996, Andrew Sambainis made the first breakthrough. So he showed that there is a private coin protocol which can do equality with square root n plus square root n bits. Okay. And then we started developing the ideas behind that. So, okay, so the first idea would be, can we reduce the number of bits of the public coin? So actually, there's a generic way of doing it, but for this protocol, there is a very nice explicit way, and that was using error correcting code. So the idea is Alice will encode her input x, okay, into a code word cx. So this is an internal computation. Only Alice can see cx, and this is in fact a deterministic computation. And all we need are error correcting codes, okay, that take as input n bits, and let us say the output is some 1000 n bits. Okay, and okay, let us say the output is some 100 n bits. And what we require is the error correcting code has constant rate, so the blow up is only constant, which is 100, and the error correcting code has constant distance. So distance means that if x is not equal to x prime, cx will disagree with cx prime in 1% of the locations. So in n out of 100 n locations. So there are error correcting codes with constant rate and constant distance. This is a non-trivial result from coding theory. Let's believe in it for now. And so Alice encodes x into cx, Bob encodes y into cy, and then we did various attempts. Okay, what we can do, but okay. But first, let us reduce the size of the public coin. So now the public coin R, okay, is a bit string of length log of 100. Okay. So R is actually a random location in the code word CX, okay, or equivalently random location pointing to code word C. What Alice does is that she takes this public coin R and sends the R bit across to the referee. Bob, you can see the same R, sends the R bit of CY across to the referee. The referee does the same thing. If the two bits are the same, output equal. If they're different, output unequal. Now again, if X is equal to Y, it's clear that the referee will output equal at probability 1. So the success probability of this is 1 if X is equal to Y. If X is not equal to Y, what happens? So if X is not equal to Y, then I know Cx and Cy differ in 1% of the locations, n out of 100. So with probability 1%, this random location R will point to some place where Cx disagrees with Cy. So there is a probability 1 by 100 that Cxr is different from Cyr if X is not equal. Okay, so if X is not equal to Y, with probability 1 by 100, I succeed. Okay, or in other words, with probability 0.99, this protocol fails. So what is the worst case failure probability? If X is equal to Y, failure probability is 0. If X is not equal to Y, the failure probability is 0.9. But there is no cause for worry, right? With probability 0.99, the failure, okay. So with probability 0.99, there's a failure probability, but that's no cause for worry because we'll repeat this protocol t times, okay, and then the failure probability will reduce from 0.99 to 0.99 to the power t. So very quickly you can bring it down to some small constant, and still the communication complexity, okay, so is constant. Let us say to go down from 0.99 to 0.001, okay, you just repeat it constant number of times. So the protocol is okay same as before. So instead of one random location R, I have R1, R2, RT. Okay, so chosen independently. So T independent locations, and the probability that all of them fall into the bad set, the 0.99 set, is less than 0.99 to the power T. So by taking T to a large enough constant, we can drive the failure probability down to let's say less than 1%. So again, I get a protocol, okay, with a small failure probability, public coin, but now the public coin was only order log n, okay, and the message complexity is order. And then we use this idea of error correcting codes to design a private coin protocol. Okay. So in the private coin protocol, recall what we did was Alice computes her code word CX, of course, but she and the code word was 100n bits long, but she doesn't write it as a bit string of length 100n, but she writes it as a 10 square root n by 10 square root n matrix. Okay. So choose your favorite ordering linearization of the matrix, let's say row major form, and then CX is the same bit string of length 100n, but written as a matrix in row major. And Bob does the same with CY. And now Alice's strategy is the following. Alice chooses a random row index I, and she will send to the referee the index I and the entire contents of the row I. So, so what is the complexity? From Alice to the referee, she sends a random index I, which is log n bits, and the entire contents of the ith row, which is square root n bits, 10 times square root n. Bob chooses a random column j and sends to the referee the index j and the entire contents of the jth column. Okay, so same complexity, log n plus square root n. And what the referee does, the referee now gets I comma j, okay, I from the Alice, j from Bob, and then she just looks at the ijth location out here. Okay, so remember, she's also got the ith row of Alice, so she will look at the jth coordinate here, and the referee has got the jth column from Bob. She'll look at the ith coordinate, and then she'll just check whether these two entries, the two bits there, are equal or not. And then we argued that this will be the same analysis as just before. So if X is equal to Y, failure probability is 0. If X is not equal to Y, failure probability is 0.99. That is because whatever the row index I is and the column index j is, they will intersect in exactly one location. And this location will be uniformly random location from 1 to 100n. So with 0.01 probability, it will be a location where the two code words differ. With 0.99 probability, it will be a location where the two code words do not differ. Okay, so the failure probability is 0.99, but then you can drive it down the same way as. So you can repeat it constant many times. That just blows up all the message complexities by constant, but it still remains a private coin protocol and justifies the statement that equality can be done in square root and plus square root. Is this clear? Yeah. Okay. So then finally, we had proved a matching lower bound. So so within a year after Ambainis's results, Ambainis just gave the upper bound, square root and plus square root. Then two papers prove the lower bound. I mean, but the proofs were, I mean, are rather difficult and essentially combinatorial. So and then I mean, much later, in 2015, Gavinsky, Clock, and some Botesh, I think, gave an information theoretic lower bound, which is probably the shortest, cutest proof of this. So that's what we discussed in class. So let's briefly recap what the idea was. Okay. So the idea was that we'll first put a probability distribution on the inputs. So put the uniform distribution on bit strings of length n, and this random variable we'll call x. Now consider the behavior of the private coin protocol when I feed the same x to Alice and Bob. Okay. So I choose a random x and feed the same x to Alice and Bob. And then I get some messages. So they are random variables that I'll call mx and nx. And now I consider a different run of the protocol where Alice behaves as before, but Bob. So remember, Bob has got a random bit string x, which happens to be the same as Alice. Okay. Now Bob is required to send not just one message, but t independent copies of the message. So the input to Bob is the same x, okay, that doesn't change, but she uses fresh private coins to generate the second message n2, then fresh private coin to generate the third message n3 up to t. Okay, so we require Bob to generate t independent copies of his message. And then we had this analysis. So we looked at the mutual information between mx and n1x, n2x, ntx. And then because mx is supported on a bits, right? The message, let us say Alice's message is a bits, Bob's message is a bits, is b bits. So trivially, I have a greater than equal to the mutual information. And then I split this mutual information into mutual information. This is the channel mutual information between mx and nix, condition on the prefix n1, n2 up to ni minus. So I use the equality of the equality property of this chain rule. And then just by averaging, I can conclude that there exists some index I naught such that the mutual information between mx and n I naught x, okay, this should be I naught here. Fine. So the mutual information between m and n I naught x, condition on the prefix, is less than a by 2. Okay. And remember, let's say I'll take t to be 100 times a or something. So I just drive it down to very small constant. Okay. Then comes the really clever, well, I mean, this setup is very clever already. And then comes the crucial part of the argument. So this conditional mutual information, we'll just treat it as an expectation. So this is an expectation over instances of the first I minus 1 messages of Bob, which I'm calling n1, n2 up to ni minus 1, of the mutual information between m and ni0, condition on the prefix of messages being fixed to this bit string. And this is the same as the condition in mutual information, so it's less than A by T. Okay. So what does this mean? This means that there is a setting of bit strings for the first I minus 1 messages, where such that now I look at the resulting probability distribution. So once I set these bit strings, that will bias the probability distribution of X, which will in turn affect the probability distribution MX and I0X. So I do all that, and this is what I conclude, that there exists a setting of bit strings of Bob's messages. First, I0 minus 1 of Bob's messages, which I will call now N1, N2, Ni0 minus 1, such that the mutual information between N and the ith message from Bob, Ni0, condition on fixing the bit strings of the first I0 minus 1 messages is less than A by T, so less than 0.00. But now what does this mean? So let us look at the amount of bias we have placed on the input random variable X as a result of fixing the first I0 minus 1 messages of Bob. Okay. So earlier, the input random variable was uniformly distributed bit strings of length n, so its entropy was Hx. But after fixing the first I0 minus 1 messages, okay, the entropy in general will go down. It will go down by how much? So how many bits have I fixed? So remember, each message of Bob is B bits long, and I fixed some I0 minus 1 messages. So at most, let's say T messages, even T minus 1 messages fixed. But I'm giving a crude lower bound T. So I fixed TB bits, okay, which means the amount of entropy that remains in X is N minus T. And think of T as 100A or something, so N minus 100A. Now, so what does this mean? So let us look at the input random variable X after I have fixed this prefix of a message from Bob. So I bias the input random variable X. So let us say that X is mostly concentrated on a subset of strings, which I've denoted by this cartoon diagram. Okay, X here is the same X out here. It's mostly concentrated. But suppose okay, N is larger than something like 10 times TB. So N is reasonably larger than TB out. So there's enough entropy left out, okay, in the input random variable. And so what I'm saying is there are several inputs, possible inputs X, X prime, X double prime, okay, which lie out here. And then I consider what is the action of the protocol when X and X is fed to Alice and Bob. Okay. Now saying that the mutual information is small, okay, so remember this mutual information is less than 0.01. So I can apply Pinsker, which says that the message of Alice for a typical X, so typical X consistent with this fixing of the prefix. So message of Alice for, let us say, a typical X from this set is almost independent of X. That is what saying, that is what it means, saying that the mutual information is small. So, or a little more precisely, the message that Alice sends for little X is very close to the average message that Alice would send when I'm averaging over all X from this set. So Alice's message is almost independent of X. So that means the message that she sends for X and X prime are almost the same. Similarly, the message that Bob sends for X and X prime are almost the same. So then I ask, what would the referee output if one feeds X to Alice and X prime to Bob? Okay. So that gives a contradiction because Bob's message for X prime is almost the same as Bob's message for X. But when the referee gets Bob's message for X and Alice's message for X, he will output equal. Okay, but how can he do so? Because X is not equal to X prime, and this is a contradiction. So the contradiction came because we assumed that there was enough entropy left in X. I mean, there were several inputs consistent with it. Okay? In particular, at least two, X and X prime. So N was larger than T times B, reasonably larger than T times B. So the okay. So So this gives the contradiction. But what is this condition? N larger than, let's say, 10 times TB. Okay, means that AB is less than 1000 n upon 1000. And if you want to equalize the messages of Alice and Bob, you would prove that you would have just shown that A is less than square root. So this was the proof. So questions, Hari?
Yeah, what does it mean to say that there is enough entropy left in the X?
Yeah. So, well, I've conditioned on fixing this, right? So look at the random variable X after I have fixed the prefix of Bob's messages. So it's no longer uniform on all the bit strings.
Okay, yes.
So it's a different random. Yeah, I'm just talking the entropy.
So it is the difference which is caused because of the non-uniformity. Okay, yeah.
Yeah, I mean, this is a crude lower bound. That I mean, I have fixed TB bits, so the entropy of X can go down by most TB. Standard, I mean, these are standard inequalities. Good old Shannon entropy. So what I want is basically, I mean, if n is, so I want n minus TB to be, let's say, at least a large constant. Okay. So saying that the entropy is a large constant means that there are, I mean, this probability distribution, the bias probability distribution, is not concentrated on just one point. Okay. It has enough support on several points. Actually, I just want 2 points, X and X prime, two different points. Okay. So that's it. So yeah, so well, to be a little more precise, maybe not two, but maybe several of them. Okay. The reason is I have to use Pinsker and argue that for each X, or let's say for most X's, Alice's message MX is approximately the average message. Okay, within some, I mean, L1 distance of, let's say, 0.1 or 0.00, whatever. Okay. So this will not hold for every message X, but this will hold for most message X. So there's a little bit of Markov there. So that loses another constant fraction of input. So let us see if X after this fixing was had support on at least 100 inputs. This Markov might lose another, let us say, even half of them. So so I know there are at least 50 such X prime, X double primes, okay, where the message M X is very close to the average message M. So finally, what I want is there are two distinct X and X prime where the messages are almost the same. Okay? And similarly, the same thing for the same XX prime for Bob. Okay? So you see that, I mean, there's one Markov here, one Markov here, and I want 2X and X prime where the messages are the same 2X and X prime where Bob's messages are almost the same, and then you are done. So yeah, so maybe you lose some. Yeah. So like you lose because of one Markov here, one Markov here. So you get a good set of inputs here. Good set means the message is almost the same. A good set out here, they should have a intersection of size at least 2. So yeah, you see, I mean, how much you lose once you formalize these markers. Yeah, so it will be good exercise to, anyway, I mean, so over the weekend, I'll come up with a problem set. So maybe, I mean, I'll give this, suggest some steps which you have to fill in to formalize this proof and complete. Okay, further questions? Okay, if not, so we will continue this topic, but we'll move to what is a really interesting part. So we have proved, so far all we saw is that any private coin protocol requires square root and bits of message. Now, what we want to do is we want to address the direct sum question, which I had just mentioned at the end of last lecture in passing. So, okay. So what is the direct sum question? So this is Alice, this was Bob, this was referee. So in the direct sum question, Alice gets not just one x from the outside, but she gets some tx's from the outside. So each x is a bit string of length 10. Similarly, Bob gets ty's. And then they send some messages. And this message is, of course, depending on x1, xt. And what will the referee output? The referee will output his guess of whether x1 equal to y1 and whether x2 equal to y2. So let me write this. So the aim of the referee is to output whether x1, okay, so equal to y1, x2, okay, equal to y2, okay. So on, his guess of whether xt equal to y2. So the output of the referee is no longer 1 bit, but t bits. Okay. The ith bit being the referee's guess whether xi equal to y. Okay. So this is called the direct sum problem for equality. Direct sum for the equality function. So t independent instance of equality have to be solved. And the question is, what is the private coin communication complexity? Okay. Is the question clear? Yeah. Okay. So let's continue. So okay. So first, let's say, okay, what happens if they're deterministic? Now, if they're deterministic, I mean, there is no doubt at all. I mean, the deterministic complex of equality was n plus n. And now instead of like one input, the t input. So let us say Alice, okay, concatenates her input to make one single bit string of length tn bits. Bob does the same, okay, and now I mean, we want to know if this tn bit string of Alice is equal to the tn bit string of Bob. Just that, yes or no. Okay, I don't want to know whether the individual parts are equal. I mean, that's a stronger question to ask. Okay, I'm asking an easier question. I just want to know if all the parts are equal or there is at least one part which is unequal. Okay, even this would take tn bits, right? Because the communication complexity of equality was exactly the input. Okay, so even this would take tn bits. So if you're talking deterministic protocol, direct sum pool. Direct sum pool means you need t times the amount of resources. Okay, so let me write down. So question is so this is the direct sum question, and then what we get deterministic. Trivial. Okay. But what about private coin algorithm? So that is where this thing gets interesting. Okay, so recall how we showed that direct sum holds for deterministic. We just considered a simpler problem. I said, okay, I don't want to know t bits of answer. I just want to know one bit of answer, which in fact in like more sophisticated language is just the end of the bits out here. Like I want to know whether all these answers are equal or at least one of them is unequal. So I want to know the end of this. Okay? So I'll say by reduction to end of the t answer. So I can take the same strategy for the private coin algorithm. Okay, So private kernel algorithm also I can say, oh, like I will reduce to the end. But then what is the complexity I would get? Okay. So what is the lower bound? Any answers? If I just reduce to end, okay, so pause the recording and I'll give you a few minutes to think about it.
I have a question. Does
Yeah.
it require only n bits?
Huh?
Only n bits?
N bits. No, I want a lower bound. Yeah. So there was for private kernel algorithm, there was a tight result of square root n, right? So I mean, why would you get n? And so and the t also has to come into the picture somewhere, right? Because for
Yeah.
deterministic it was tn. T bits. Yeah, right bound of tn bits. So similarly, what would you expect the private kernel algorithm?
If you do the same kind of thing, then it should be like t root n bits.
T root n. Well, so let's see. Okay. So reduction to n means I'm just thinking of equality for bit strings of length tn, right? That's that's what this means in simple English. So but we have a lower bound of square root tn, right? Or square root tn. So which is equality for tn bits. That's all. Okay, so the reduction to n would give a lower bound of square root tn. But then the question is, but is there a protocol which can do it in square root tn? But then the only thing we seem to be able to do is to repeat t instances of the private coin protocol for equality. So the upper bound that we are getting is looking like t times square root of n. In fact, it'll be a little worse because it was t times square root of n. It was square root of an upper bound with constant probability of error. Now, if you have to tolerate like t independent instances, so the probability of error is increasing from epsilon to t epsilon, right? So if I want the probability of error to be small, less than epsilon, then I have to ensure that each single instance has smaller than epsilon probability of error. So let us see what it is. So private coin upper bound. So so first naive upper bound would be t times square root n, but there's a catch here because it was square root n, let us say with 1% probability of error upper bound, and I want protocols with 1% probability of error. If I repeat it independently t times, then that 1% will become t%. Right? I don't want that. So what I have to do is, for one instance, I have to reduce the error probability to 1 by t, whatever, to 0.01 by t. So that means even for one instance, I cannot do it square root n, but I have to repeat the same protocol something like log t times to reduce the probability of error.
Log t times, yeah.
Yeah, that's what I've written, log t, okay? So because error probability of single instance reduce to, let's say, order one. Order one. So now a single instance will take square root and log t bits, and then you do t instances, so t square root and log t. So that's what the upper bound looks like. But the lower bound is only square root t. Okay? So let us say we don't bother so much with log t factor, but we don't like that there's a square root t dependency and a t dependency. So the direct sum question is, do you need t times the resources? Okay, and we don't, the upper bound looks like, I mean, we cannot do better than that. Okay, at least for equality. So we upper bound suggests that we need t times the resources, but the lower bound doesn't quite match up. So the question is, where is the truth? Is the truth closer to the lower bound, or is the truth closer to the upper bound? Okay. So this was open for a very long time, and so this is called a direct sum problem. And till 2001, not much was known about direct sum for private coin, or in general for randomized algorithms. So for deterministic algorithms, often the answer is trivial, okay, like this. Okay, a few examples were known where direct sum doesn't hold, and in many cases direct sum holds. That was known. Then some things were known for public coin protocols, and but for private coin protocols, nobody knew a thing. So there was a breakthrough in 2001 which showed that the truth is actually closer to the upper bound. So in other words, one can prove a lower bound of t times square root of it. So like that.
This was Radhakrishnan Jain Sen.
No. This is the one which started on. This is Chakravarti. He worked Yao. Same Yao. T square. Oh,
But you guys also had some sort of a result on direct sum, right? The paper where the substrate theorem appears.
So we wrote the next paper after Chakravarti et al. Okay, where we so Chakravarti et al. Was really tied only to equality. So then we sort of made it general for I mean very large class of functions, essentially all functions, but for one round protocols, simultaneous or one round protocols, or more general constant round protocols. If you have t rounds, things started decaying. And then the final thing was done by Braverman and Rao, uh, maybe 2000, 2009, where they handled the T-round protocols nicely. So, yeah. So for large class of functions.
So it is known that there is no protocol that achieves square root Tn.
Yes. So this is what we're going to see now. Okay. And this is where we'll bring in one-shot information. So if you look at Chakravarti et al.'s paper, you will not see one-shot terms at all. Okay. So this proof is basically a modern way of thinking about the. Even if you see our paper just after that, you will not see any one-shot terms. Okay. But
Chakravarti spelling is
I think this is how that guy spells it.
Oh,
because
okay.
It is not your spelling. This is not Shantan Chakravarti. This is Amit Chakravarti. I think he spells it this way. Anyway, let's not bother about how to spell it. Amit Chakravarti, Yao Yun Shi, some guy called Andrew Worth, and then Andrew Yao. Okay. So here is the idea. Any questions, before we proceed? Now we are going to prove t times square root. Okay. No questions? Okay. Good. So let's try to prove it. And okay. So Chakravarti et al.'s proof, I mean, paper was seminal in the sense that they really brought in information theory and they showed the power of information theory. Okay, so I mean, they used just Shannon mutual information and like Shannon entropies and things like that. But and since then, all the progress in direct sum has happened through information. So our work and Braverman, Rao, all of them are using information theory.
Pranab, can I ask you something? Sorry, I joined slightly late. Can you just in a minute tell me what the direct sum problem is and what is the task?
This is direct sum problem. So you haven't missed anything. I just recapped the previous lecture. This is the direction.
Oh, that's it. Okay.
That's it. Okay. I mean, you have t independent instance of problem. Do you need t times the resources for one instance? Okay. And we are just doing direction for equality in
Okay.
simultaneous.
Got it.
Okay. So, okay. So let us see. So what we will do is so let us analyze the encoding behavior of Alice. So Alice is a private coin algorithm. So let us analyze the encoding behavior of Alice. Once we put in uniform and independent bit strings x1 to x2. So in other words, what I'm going to do is, so capital X is the uniformly distributed random variable on bit strings of length n and like t independent. And Alice's messages like is the random variable that I'll call n, and it's of course a function of x1. Yeah, x2 LT. So in other words, yeah, so message is n. So basically I have a joint random variable which I'll be analyzing x1, x2. Good. Now I will look at the mutual information between x1, x2. So this is the mutual information between Alice's input and the message. Okay. And then I can use the chain rule. Right? So this is some I. This is Shannon mutual information. Okay. Xi colon n condition on the prefix x1, xi minus 1. Right. So far so good. Okay.
So the only reason the conditioning appears is because the message is a function of all the random bits.
Yes.
Otherwise,
yes.
Okay.
Yes. So the question is yeah. Yeah. So the question is I mean, if Alice does clever things, can she? I mean, get by with less than t times square root of. Okay. So yeah, so that's what we're trying to. And there are other instances which Alice can do such clever things. Okay? So she's not constrained to just repeat her protocol parallelly some t times. Okay. So now, so this is nothing but. So I'm removing the conditioning, and now I'll explain why I can do that. Okay, that's it. The conditioning x1 to xi minus 1, I moved it to the side of it. Now I can do this because x1, x2, xt are independent random variables. Now why is that? So let me analyze this. So what is this? This quantity, the mutual information between xi with respect to m and the prefix. So this is nothing but the mutual information between the xi and the prefix, plus the mutual information between xi and m condition on the prefix, which is this time. But the mutual information between xi and the prefix is 0 because the x's are independent. Okay, so hence this quantity is equal to the condition. Did you follow that? So this is because And now I'll use data processing inequality for channel mutual information. So this is greater than sum I.
So you're going to
mutual-
trace out the x1 to xi minus 1, yeah?
Yeah. Okay. So this is greater than equal to sum I mutual information between xi and n. Okay. Yeah. And yeah. And of course, let us say Alice's message is A bits. So okay. So remember, I want to prove a lower bound for A and B. Okay. So Alice A bits of the message. What the hell? How do you select this?
You have to click the hand. Remember, you have to click the hand.
Hand?
Yeah.
Huh.
Huh? What? Okay, maybe not the hand.
No.
Last time Hari Krishna suggested something which worked, I remember.
Okay. So anyway, so let's not spend too much time. That this indicates. So Bob is B bits of message. As before. So what is this giving me? So what have I concluded? Remember the mutual information between x1 dot dot xt colon n is less than a because n is supported on a bits only. Okay? So this means that there exists I naught, okay, some location I naught such that the mutual information between x I naught with n is small. Okay, so this is less than a by t, right? Okay.
No, sorry, I didn't follow this. So this summation is like upper bounded by the mutual information of all the message, all the message with all the bits, right?
Yeah.
And that is upper bounded by a because the message length itself is a, right?
Yeah.
And you're
That's
saying that. Acha,
So-
okay, got it.
This is the usual thing. We did something similar when we were again doing equality, but trying to show
Yeah,
the
got
square
it,
root
got
and
it.
lower bound. Okay. So here is one reason why information theory is so useful for direct sum. That's already apparent here. And I guess this is really, I mean, the main insight of those authors. And so Alice could have done a very clever encoding strategy. We have no control on the cleverness of Alice. But this mutual information has this direct sum property. If you put in like independent random variables here, okay, you get this inequality. So no matter what Alice does, there is some index I naught about which her message is revealing very little information. Okay. So what is this saying? Let us understand the import of this. Now, remember in this protocol, the messages are expected to be long. Okay. I mean, I know the messages are at least square root tn bits long. They are way above square root n bits. So the messages are long. But this message, this long message has small information about xi. Okay. But what is this mutual information quantity, right? In this mutual information quantity, the other x's don't appear. That means I'm averaging over the other. Okay. So in other words, this message M of Alice has small information about xi naught, provided I average over the other messages. Okay. So what is this giving me? So let us now construct a new protocol for equality for one instance. Okay. So what I do? So the one instance, some x is coming on from outside. I'm going to feed it to the I know Alice is going to feed it to the I naught coordinate. So input X, which is coming from the outside, becomes Xi naught. Okay, and similarly, Y I naught. Yeah, so you need something like the same location I naught should have small mutual information for Alice, for Bob. So there's some Markov factor
Jita,
of 2.
Jita, can I call you at 2? I have a shit ton of things.
Stanton, unmute yourself. Yeah. Okay, so now of course I want that the same index I naught gives small mutual information for both Alice and Bob. Okay, so you do a Markov and all that. I mean, you can ensure that this is the case. So, okay. So I identify this location I naught, where the mutual information between Alice's message and X I naught is small. Mutual information between Bob's message and Y I naught is small. Okay. But note that these mutual informations involve averaging over the other coordinates. So what are the other coordinates? Alice will just, so this is a new protocol. This is a new protocol for one instance of equality, which I am creating from the direct sum protocol. So the input X from outside is fed into I naught. Then Alice chooses the other Xi's, okay, uniformly and independently of her input, of this Xi. And Bob also does the same thing. He chooses the other Yi's independently and uniformly. And then Alice is going to run the direct sum protocol on this. Okay, so here the only real input coming from the outside is Xi naught. And now we can ask what is the mutual information between the message and Xi naught, and between the message N and Y I naught. I know that these are small, but note that this is a protocol with huge message lengths. Okay, the message lengths are coming from the direct sum protocol, so they're at least at least square root t times square root of. And now I'm only going to analyze from this protocol. I am inferring some very inefficient looking protocol for one instance of equality. Okay, so this is a protocol for one instance of equality with huge messages. Okay, but the messages carry very little information about the. So this is the scenario I'm working. Anyway, I'm assuming the correctness of the direct sum protocol for equality. So the referee gets something. The referee gets some. I mean, all the t answers. I mean, whether the like the jth xi is equal to jth y or not. He ignores all the other answers. He just looks at the answer for the I naught part and he outputs that.
So then M is independent of x1 through xi naught minus 1 and xi naught plus 1 through xt. It is only correlated with xi naught in the new protocol.
No. So M depends upon all of them. Okay.
Even in the new protocol that you are
In the new
creating now.
protocol also. Yes.
I think what is happening is the following. So Alice gets one bit X from outside. Okay.
Not one
And
bit.
Alice
One bit.
says that, okay,
One bit string.
one bit, yeah,
xi naught, yeah.
xi naught, and she says that I'll place this at the I naughteth place, at the I naughteth
Location.
yes, I naught location, right? Everything else is sampled uniformly at random using Alice's private coins, and those are appended together to create this big bit string that is processed using some clever protocol which we don't know, but which has this following guarantee, and what is produced is this M, and that M is what is sent to the referee. This is what is going on.
So we don't know how M explicitly depends on
No. We only have the mutual information guarantee.
Okay. Yeah. So the point I would emphasize is this is a protocol for one instance of equality on n bits. Okay. Its correctness is same. I mean, same as the correctness of the direct sum, maybe even higher, because I mean, I don't care if the direct sum protocol fails on the other coordinates. Okay. So its correctness is at least the correctness of the direct sum protocol. Okay. Correctness is more than 1 minus epsilon. Okay. Its protocol on n bit inputs. Its message lengths are huge. I mean, A bits, and A is quite large. But the mutual information between this huge message and the true input xi naught is small. So this is the scenario I'm now working. Is that clear? So should add that. So this is protocol. Okay, so I have come to that. Now what I'll do is that I'll do my message compression technique, which we did a few lectures back. Okay, so how to do that? Okay, so the mutual information is small, which is less than A by T. Now, if the mutual information is small, the max mutual information is also small. So this is the substrate theorem. Okay, so so let me write that down.
Yeah, so you'll be using the lower bound part of the substrate theorem, right? That you have a upper bound on the relative
No,
entropy
so which says
via
that
the Dmax.
well, I mean, I'm using the fact that Dmax epsilon is less than D1 by epsilon. So, right. It's less than.
But that gives you a lower bound. You want to say that the relative entropy is D1 is
not a
also
lower
small.
bound. That's an upper bound. So let me write down. So Imax epsilon is less.
Yeah.
Okay. So yeah, I mean the substrate theorem holds for the divergences. Now we are only looking at the mutual information, so the special types of divergences.
Right. Yeah.
No problem.
Yeah.
So
yeah.
Imax epsilon of xi. I'm just writing xi instead of xi now. Xi colon m is less than or equal to I xi colon m divided by epsilon. So this is substrate. So
Okay. I see very good. So you're going to say that my message
so this is
compression
less than or
protocol
equal to A by T epsilon.
right. You're going to
Think
say
of
that
epsilon as
my message
0.001 or
compression
something.
protocol.
Yeah.
Hello.
Yeah. You saying something? Hello. Yeah. Are you saying something?
Am I audible? Yeah. I was saying that is this the direction that you're going? That I have a message compression protocol which gives me a compression of the smooth max between xi and m, right? And I have a bound on the smooth max between xi and m via the substrate theorem. So I can say that the compression is at most A by T. That is what is going.
Yeah.
Okay.
Yeah. Okay. So now what I've got, like I have this inefficient looking protocol for equality, which has huge messages, but its max mutual information is small. Now, channel mutual information is small implies max mutual information is. So now I can do the message compression theorem. Okay. So what is the message compression theorem telling me? So we'll change the color of this. How does one change the color of it? Doesn't matter. Okay. So maybe I'll use dotted. Okay. So I get a similarly the dashed ones are the compressed protocol. So now the message compression protocol shows that I can compress the messages, but I need public coins. But this is a different type of public coin. This is not a public coin between Alice and Bob, but this is a public coin between Alice and referee.
Alice and referee.
Yeah, and an independent public coin from Bob to referee. So let me indicate the public coin also. So I'll have a different thing. Dash dot. So that's the public coin. Okay. So this is BR public coin. This is AR public coin. Okay. So I have to put in an additional resource, share public coins between A and R, B and R, and then I can compress the messages, okay, to the max mutual information. So this becomes like A by T epsilon. Okay.
This epsilon comes only because I'm dealing with the smooth max, right? Otherwise, the epsilon wouldn't be there.
Yeah, but I mean, I can only relate Imax epsilon to I. I cannot relate Imax to I. Follow that, right?
Yeah.
So I have to choose some message.
Imax can be anything. I'm pretty sure you can come up with counter examples where Imax.
Yeah, Imax can be anything. IMAX can be anything. I mean, we know all we know is less than infinity, but that's
Yeah.
it can be anything. Yeah. Okay. So I have now brought down the message. So think of epsilon as a very small constant. Okay. So this is still a by t, and that is still b by t. Okay. So now from this protocol with long messages, I have now come to a protocol with very short messages. Okay, by message compression, but I had to use this public coins, AR public coin and the BR public. Okay. Now, the next step is I remove these public coins. So this is actually, Shantan, what you were referring to last time. So we'll have to now see this in some detail. So let's come to next step. Right now. So, newer protocol with short messages is A by T epsilon. So this is a newer protocol. So next step is, okay, I claim that shorten AR public coin to log in bits BR. The next claim is that I can shorten the AR public coin to log n bits and the BR public coin to log n bits. Okay. So how is that done? So this is again a standard technique. I mean, this was first done by Newman in 1991, but it's just, I mean, Chernoff. Okay? So once you get the realization, I mean, it's quite easy. Okay, so what is the idea? So I want to shorten this public coin. Okay, I mean, the public coin, let's say, is huge. No idea what it is now. Remember, I mean, message compression had a huge public coin. So the public coin is huge. Now, let us say I take t independent copies of this public coin, and same for Bob, the BR public. T independent copies.
Can I take a guess?
Okay.
Okay. So I'm going to use Badhya paradox kind of stuff. So let's say I repeated some k times. Okay, and so
There's no Badhya paradox. I don't want consistency between AR and BR. These are independent public coins. It's independent.
No, I want to be able to say that Alice and Bob agree. Alice and referee agree on one kind of randomness, right? That's what I want to say, that they know that the other guy has this specific setting of the coins.
So that's just instantiation. It's not Badhya. I mean,
yeah.
At the moment, I don't even want to remove public coins entirely. I just want to restrict the size of the public coin to log n bits.
Okay. Please go on then.
Yeah. Okay. And then the next part will be trivial, but yeah, at the moment I want to do it. And then it will connect to why we could do this for the equality case when Alice and Bob share the public coin. As I said, the difference is AR sharing public coin, BR sharing public coins will turn out to be benign. Okay, but AB sharing public coins was the killer. We'll see why that's the case. Okay. So the idea is, here's a public coin using many bits. Now let us say I take t independent instances of this public coin. Then the error probability. So the error probability was a small constant of this protocol. So take t independent instance of AR public coin, t independent instance of BR public coin. So averaged over all these independent instances, AR and BR, the error probability. So what is the referee going to do? The referee is going to look at the answers coming from the first instance of public coin, second instance, all the way up to t instances, and he's going to output the majority. Okay. So simple Chernoff will tell that the error probability will go down exponentially in t. So 2 to the minus t. Now, this is the error probability for one input instance x comma y. Okay. Now, of course, the number of input instances, that 2 to the n of them, 2 to the n of them. So the total number of input instances is 2 to the 2. Now, if t is larger than 2n, let us say t is some 10 times, then the error probability for a single instance is less than 2 to the minus 5n or something. Okay. So this is the error probability for a single instance, x comma y. For another instance, x prime comma y prime, the error probability is still less than 2 to the minus 5. So now I can do a union bound over all input pairs. So what does this tell me? This tells me that even after doing a union bound over all input pairs, there are overly many settings of public coins for AR as well as BR, such that the probability that the probability that the majority strategy makes an error on any input is exponentially smaller. So, in other words, what this says now.
Can I ask for clarification? So you had some public coins, the AR public coin, and you're saying that I have many repeated independent copies of the AR public coin, no matter how long each of them are, and the same thing for the BR public coin. And then you're going to say that, okay, since I have many copies, say T copies, I'm going to use Chernoff bound, and Chernoff bound will tell me that my error probability over each of these coins is at most e power minus T, right? Or maybe e power minus. So if I set this T to be like 10 or 100n, it's e power minus 100n. Great. Now my total number of message pairs is 2 to the 2n. Possible message pairs is 2 to the 2n. So a union bound will tell me that error for this protocol over all message pairs, for all message pairs inside the probability, is at most 2 to the 2n by 2 to the 10 to the 100n, which is itself exponentially small. So yeah, that's what you're saying, right?
Yeah. That's fine.
Okay.
Yeah, that's what I'm writing here. With non-zero probability, there's an instantiation of AR and BR public coin. Okay. Which is correct. Input. So even after the union bound, it's exponentially small. Actually, all I care at this point is after the union bound, it has to be non-zero. So this says that if I take t equal to 10n, with non-zero probability, there's an instantiation of the AR and the BR public coins, which is correct for all the 2 to the 2n input pairs. Okay. So fix this instantiation. And so what I've got, so now there are 10n instances of the AR public coin here, 10n instances of the BR public coin out here. Okay. And now instantiation means the public coin is fixed. So there are 10 fixed coins, 10 fixed coins out here. And now, so after fixing them, then yeah. So
no, that's it. That's it, right? Alice just has to point to which one.
There's one little thing. So after fixing them, then I mean there is no error for any input pair. Okay, remember what was the referee doing? The referee was taking a sample average over these T public coins of AR and T public coins of BR. Okay, so this instantiation strategy does not totally vitiate the public coin, but reduces the public coin. So how much a public coin remains? Just the choice of which instance to take out. Okay. So now, after instantiating public coin, the sample average is only over a set of size 10. Okay. So what I want to say is sample average for Chernoff is now over set of size 10. And so So public coin AR is now log n bits. Similarly for PR. Okay. So so note that the original public coins were huge strings. So after instantiation also they are huge strings, but they're not fixed. Okay. So there are 10n fixed huge strings between A and R, 10n fixed huge strings between B and R. And what do I know? If I do the sample average over this fixed 10n strings, the protocol is correct, okay, with high probability for all inputs. So this is
very subtle, by the way. I mean, this is exactly where I had tripped up. So the point is that even before the protocol starts, you have fixed the public coin. The public coin is no longer a random thing on which you can do an averaging. The 10n arrays which hold the public coin, they have been fixed, and you're not really counting the number of bits in them. You just
yeah.
So
I just want that there are these 10n arrays, and if I do a sample average, so which was the channel strategy of the referee? Okay, so I have to do a sample average over them. Okay, and that will give me the correct answer with high probability for every input.
As in one can say that even before the protocol starts, these three parties came together, they agreed upon some preset public coins.
Yes.
And then they went away and started doing all this
yeah,
stuff.
and
This
then
is
they
like
went
the
and started
random
the protocol. Yeah, they agreed
Yes.
upon this fixed 10n strings for AR, fixed 10n strings for BR. They did the protocol, and all that has to be done is Alice, the new public coin will be which of these 10n to take, and independently which of these 10n to take. Okay. But now what Alice can do is that, because the new public coin is just one out of this 10n, she can just toss it herself as a private coin and send it along with a message. And similarly for Bob. And this is where I'm using the fact that the AR public coin is independent of the BR public coin. So this index, which one of these 1 to 10n to take, and this index, which one of these 1 to 10n to take, they're independent random variables. So they can be now made into private coins. So now what I'm going to write is plus log n. Okay. Here also it's plus log n bits. Okay. And this, to remind you, where did this log n come from? So this is Chernoff reduction public coin to 10 instances. This came from there. Maybe I should just say log 10. So this is actually, I mean, just 5-6 pages long paper of Newman, but this is the clever insight of Newman, which shows how you can reduce the public to log n. Now, the point is, if this public coin was between Alice and Bob, okay, fine, you can reduce this public coin to log n. And remember, in equality, we saw an explicit way to reduce the public coin to log n. But even by these chain of arguments, we know that there's a public coin of size log n, which will do equality. But then it still remains public. I mean, Alice cannot toss those log n bits herself, and independently Bob cannot toss those log n bits himself. And then there will not be a consistency. But if the public coin is between AR and independently with BR, Alice can toss those log 10n bits herself, send it to referee. Bob can toss those log 10n bits himself, send it to the referee. Okay. So finally, this becomes a private coin protocol with for equality of n bit strings. And now, what is the bit length? A by T epsilon plus log 10n bits. Okay. Similarly, this. So what have we got? So we know that A by T epsilon plus log n. So this has to be greater than square root. Because we have the lower bound of square root n for private coin protocols free. So log n is nothing in terms of square root of n. So what does this say? This says that A is greater than T epsilon square root. Okay. And remember, I mean, the epsilon is like 0.01 or something, constant probability of error. So ultimately, I've shown a lower bound of T times square root for A. And similarly for B. Okay, so this finishes the proof of Chakravarti on the direct sum problem for equality. Questions? Okay, if not, we will stop now. And so the yeah, so we can come back to information theory and look at multi-terminal channels like multiple access channel, then wiretap channels, etc., and apply our one-shot bounds to it. Get get nice and tight bounds, nice second-order analysis in some cases, and so we can either do that, or we can see maybe one other example of where information theory like this, okay, one-shot information theory, has provided lower bounds for some computation problems. So I don't know what you prefer.
I would prefer the second one.
No, that's because you know the other one. Okay.
Yes.
What
Yes.
about Hari?
Okay, yeah. I mean, I don't have any preference. So yeah, second one is fine.
Second one is. Yeah, it's end of September. So maybe I'll do the second one because I mean the aim of this course is to do the techniques of information theory rather than applications.
Pranab, can you stay a minute after the class ends and everybody else leaves? There's something I need to inform you about. Maybe Aditya can stay.
Oh, okay, sure. Yeah. Anyway, let's stop the recording.
Yeah.